Okay, today we're still in Chapter 5. We're doing 5.4, which is using medians and altitudes. Okay, first of all, a triangle will balance at a particular point. This point is the intersection of the medians of the triangle. Okay, a median of a triangle is a segment from a vertex to the midpoint of the opposite side. All three medians of a triangle are concurrent. The point of concurrency, called the centroid, is inside the triangle. We're going to get a picture on the next slide, but these are the vocabulary words you need to write down. A triangle will balance at a particular point. So if you had a pencil and you sort of set the triangle on top of the pencil, it would balance as long as that was where the three medians of the triangle meet, which is called the centroid. So let's look at our picture. Okay, let me fill this in real quick. Okay, Theorem 5.8, concurrency of medians of a triangle. The medians of a triangle intersect at a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. Okay, the medians of triangle ABC meet at point P, and AP is 2/3 of AE, BP is 2/3 of BF, and CP is 2/3 of CD. Okay, let's look at that again. The medians of ABC, okay, I drew in the medians, and we said the definition was I go from a vertex to the middle of the segment across from it. So I went from C to halfway in between AB, from vertex B to halfway in between AC, from vertex A to halfway in between BC. And mathematically, we could say that AP, this segment right here, is 2/3 of the whole segment. So I have 2/3 here and 1/3 here. Okay, this segment is 2/3 of the whole distance, and this segment is 1/3. Okay, same with this one. This one's 2/3, this one's 1/3. 2/3, 1/3. And of course, we're going to use that ratio in some algebra problems in this chapter. All right, in triangle RST, Q is the centroid, and SQ equals 8. Find QW and SW. We know that SQ is 2/3 of SW. We know that SQ is 8. I'm going to multiply both sides by the reciprocal, which is the same as dividing both sides by the fraction. Okay, those are gone. 3 times 8 is 24. Divide by 2 is 12, equals SW. So that full length is 12, which means QW is 12 minus 8, which equals 4. Sorry, QW is 4, SW is 12. Example 2. I need a graph for this one. Hold on a second. Okay, let's talk about this one. The vertices of triangle FGH are given. Which ordered pair gives the coordinates of the centroid P of triangle FGH? Okay, the coordinates of the centroid. Now remember, the centroid is where, if we drew a line from the vertice to the midpoint, vertex to midpoint, vertex to midpoint, vertex to midpoint, centroid is in the middle. Okay, so first of all, I sketched FGH. Then I'm going to use the midpoint formula to find the midpoints of each side. First, we're going to do FH. So I'm going to find the midpoint of FH. So the midpoint the midpoint of FH, is x plus x over 2. So 2 plus 6 over 2, and y plus y over 2. 5 plus 1 over 2. So my midpoint is 8 divided by 2 is 4. 6 divided by 2 is 3. So I'm going to go 1, 2, 3, 4, 1, 2, 3. My drawing is awful. Let me check some things. 2, 1, 2, 3, 4, 5. Let's see. Oh, I can't erase that. Sorry, my drawing is pretty bad. Let's try this. 1, 2, 3, 4, 1, 2, 3. Well, that's not possible. 1, 2, 3, 4, 5. There's the problem. H is supposed to be over here. And I can't erase that. So we're going to look at the bold lines. And this dot right here is the midpoint of FH. Cool. All right, the centroid, we know, is 2/3 the distance from each vertex. Okay, so if I drew a line from the vertex awful, from the vertex to this midpoint, let's label this K. So the centroid, if we call that P, from G to P is 2/3 from G to K. I said G, I wrote H, from G to K, right? The centroid is 2/3 of the distance from each vertex to the midpoint of the opposite side. So let's do the distance. What is the distance of GK? I'm going to have to continue on the next page, just warning you. So the distance of GK is x minus x. G is 4, so x minus k is 4 squared plus y minus y. G is 9, k is 3 squared. Okay, next slide. So write this down because I'm moving to the next slide. 4 minus 4, 9 minus 3. So this should be a straight line. So if I count 1, 2, 3, 4, this is my centroid. P, and if G is 4, 9, P is going to be 4, 9 minus 4 is 5, which is B. Excellent work. There is one of these on your homework, so if you don't understand that, make sure you ask a question. 4 minus 4 squared, 9 minus 3. 0 squared plus 6 squared, 36. So GK is 6. Awesome. So 2/3 of 6. 2 times 6 is 12, divided by 3 is 4. Okay, so the centroid is 4 units down on GK. I'm going to go back and look at that. Forward again. All right, you try. There are 3 paths through a triangular park. Each path goes from the midpoint of one edge to the opposite corner, or vertex. The paths meet at point P. So point P is the centroid, right? I'll do this first one because there's 2 more for you. If SC equals 2,100 feet, find PS and PC. Okay, if you remember the definition, the centroid is 2/3 of the distance from the vertex to the midpoint. So the centroid is 2/3 the distance from the vertex to the midpoint. So we know that CP is 2/3 of SC. So CP equals 2/3 times 2,100. 2 times 2,100 is 4,200. Divide by 3. 3 goes into 4 one time. 3 goes into 12, 4. All right. So, sorry, I said CP. PC is 1,400 feet. And you can just do some simple subtraction. The original, like the full segment length, is 2,100 minus 1,400 means that PS is 700 feet. Okay, you try the next 2. Here we go. If BT equals 1,000, find TC and BC. Go. I'm pushing pause. Okay, T is the midpoint of BC. So BT and TC are congruent. So TC equals 1,000 and BC equals 2,000. Last one. Push and pause. This one's just a tad bit confusing, but not awful. We know that PA equals 2/3 of TA, because that's the definition of centroid. PA equals 2/3 of TA. Wrote it right here. So technically, PT equals 1/3 of TA. Okay, those are our fractions. PT equals 1/3 of TA. So I wrote that down. We know that PT equals 800. 1/3 TA. I multiplied both sides by 3 and solved for TA. Then I went back to the original equation, plugged in TA. Okay, PA equals 2/3 of TA, and I solved for PA. Okay, video break. Good job today. Okay, we're starting the second half of section 5.4. So we're at 5.4 part 2. I want to start out with a vocabulary word, altitude. Okay, the altitude of a triangle is the perpendicular segment from a vertex to the opposite side, or to the line that contains the opposite side. So here we have a vertex, perpendicular, opposite side. But when I have an obtuse triangle, vertex to a line that contains the opposite side. So this would be the altitude of an obtuse triangle. See how it's not actually inside the triangle, where this one is inside the triangle. So there we have our altitude from Q to line PR. Another theorem, theorem 5.9, concurrency of altitudes of a triangle. So the lines containing the altitudes of a triangle are concurrent. The lines containing AF, BE, and CD meet at point G. Okay? Those all meet at point G. The point at which the lines containing the three altitudes of a triangle intersect is called the orthocenter. Another vocabulary word. So let me draw these in. I'm going to push pause for a second. Okay, I had to fix my drawing. Let's talk through this again. Go slow, okay, and pay attention. The lines containing the altitudes of a triangle are concurrent. So the three altitudes meet together at a concurrent spot. The lines containing AF, there's AF, okay, BE, these are all altitudes. So we have AF, BE, and CD meet at point G. Now my original triangle is triangle ABC, but I drew the altitude from C, but I had to extend this line a little bit to do that because it has to be a right angle. I drew the altitude from B, but I had to extend this line a little bit to do so because it has to be a right angle. The altitude from A was easy, okay, it's inside the triangle, but I just had to extend it up, and it's concurrent, okay, they meet at point G. So point G is called the orthocenter, okay, yes, wow, let's move on. Okay, now we need to find the orthocenter in an acute, a right, and an obtuse triangle. So I'm going to go ahead and draw those. So give me a second. So there I have an acute, a right, and an obtuse triangle. For those of you that aren't used to my hand drawing or my drawing of shapes, I apologize. I think all math teachers should have to double major in art, but yeah, I'm not very good at it. So I'm going to go ahead and draw some altitudes. Okay, because remember the orthocenter is the point at which the lines containing three altitudes intersect. So we're going to do the altitudes in red. So I need to draw a line that is perpendicular to that side. A line, that's awful. Oh no, it didn't work. Let's see if I can fix that one. A line that's perpendicular to that side, and this last one's going to be a little, it's not letting me go back. There we go. A line perpendicular to that one. So we're drawing the orthocenter, which is P. I'm going to make that blue, the orthocenter. Okay? Now this next one, the right triangle, this is already a right angle. So my altitude for this side is going to be actually right there, which is sort of cool. Okay, the altitude for this side is going to be right there. And the altitude here is right there. So your orthocenter is where those three things meet, which is right here. And then the obtuse one. Okay, this first side is easy, so I'm going to do it first. Okay. Then I'm going to extend this side and extend that side, because these next ones are a little harder. There's my right angle. That looks about right. So the orthocenter is actually, I have to extend these altitudes all the way up. And this is my orthocenter. Pretty cool. Example 4. Prove a property of isosceles triangles. Okay, prove that the median to the base of an isosceles triangle is an altitude. Okay, and I left all the solutions up here. We're going to talk through it. So prove that the median to the base of an isosceles triangle is an altitude. Here I have the base. The median, which is the middle, is D, which gives us two equal sides right here. Okay, it's isosceles, so these sides are congruent too. So let's talk through this. Triangle ABC is isosceles with base AC. BD is the median to base AC. Okay, sorry, D is the midpoint, BD is the median. It goes from the vertex to the midpoint. We talked about that in section 5.4, part 1. So we need to prove that BD is an altitude of triangle ABC. Okay, and we're just going to talk about it. I'm not doing a 2-column proof. We're just going to chat for a while. So we can say that AB and is congruent to BC. Okay, because they are the legs. Oh goodness, I was trying to erase. Because they are the legs of an isosceles triangle. Okay. We also know that CD is congruent to AD because it's the definition of midpoint. And D is the midpoint. And we also know that BD is congruent to BD. It's reflexive. Reflexive. So I can put 3 tick marks there. So I'm going to turn the page. I think I have a blank slide. Oop. Sorry about that. Needed to get rid of that stuff. So we know that triangle ABD is congruent to triangle CBD. And you can go back and look at those triangles. ABD is congruent to CBD because of the side-side-side congruence postulate. Okay? So angle ADB is congruent to angle CBD because of CPCTC, ADB, CDB. And angle ADB and angle CBD are a linear pair. And if 2 angles are a linear pair and congruent, then they are perpendicular. So BD is perpendicular to AC, and BD is the altitude. Altitude. Okay, not too hard. Well, it is sort of hard, but I hope it makes better sense to you now. All right, you try. Copy the triangle example 4, which I did, and find its orthocenter. Hold on a second. So what I'd like you to do is to actually draw that in your notes, right? And find its orthocenter. So I'm going to push pause and work on this one too, and I'm going to draw in blue. There we go. It looked to be an obtuse triangle, so its orthocenter is not inside of the triangle. Okay? Another you try. What if, in example 4, suppose you wanted to show that median BD is also an angle bisector. How would your proof be different? I'll talk through this one with you. We did prove that triangle ABD is congruent to triangle CBD because of side, 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 because this is also congruent. So we can say that angle ABD is congruent to angle CBD because of CPCTC. So those angles are congruent. And because those are congruent, you can say BD is an angle bisector because of the definition. It cut an angle into 2 equal pieces. Pretty cool. Last you try. Triangle PQR is an isosceles triangle, and segment OQ is an altitude. What else do you know about OQ? What are the coordinates of P? Okay, the coordinates of P, why don't we do that one first? Okay, what do you think they are? See if you can do it. Did you get it yet? If this is an isosceles triangle, if that is equal, this is equal, the bases are equal, then these segments are equal too. Okay, O to R is the same as O to P. So P is negative HO. Okay, that one you should be able to get. So what else do we know about OQ? Well, we learned that OQ, if it's its altitude, if these two are equal, then this actually is a perpendicular bisector. Yep, that's what we know. Daily homework quiz, first 3. Go ahead and bring in the answer for 2 points tomorrow. Next 2. Go ahead and bring in the answer for 2 points tomorrow. Good job.